on the subject of wave diffraction by penetrable wedges, which we've established has been an important canonical scattering problem. Now, the problem has uses for both acoustics and electromagnetics, but for us, our original motivation came from its use as a component in convex polygon diffraction. For instance, take this numerical simulation of a plane wave being scattered by a penetrable triangle. This is useful in modeling the scattering of solar radiation by ice crystals in high altitude clouds. However, numerical simulations of this scattering can be quite expensive, computationally expensive for high frequency waves such as sunlight. This has given rise to hybrid numerical asymptotic schemes, such as those demonstrated in this paper. Now, bettering these methods requires a better understanding of the penetrable wedge problem. This is because we assume that for sufficiently high frequency, the behavior around one of these corners is like that of an infinite wedge. For wave diffraction, that is. So now let's set up the problem. We have an infinite penetrable wedge. We look for time harmonic solutions to the wave equation by assuming and suppressing this time factor. The instant wave takes the form of a plane wave, where the propagation vector is perfectly in plane with the screen and is measured by the angle theta I. This allows us to simplify the 3D problem into a 2D projection. The domain itself is split into two angular regions. The host we call omega 1 and the scatterer being omega 2. Now these are measured by the angles theta w and theta w bar respectively. These two regions have their own total wave field, phi for omega 1 and psi for omega 2. Now physically these could represent acoustic pressure fields or electromagnetic field components that are polarized so that they're parallel with the wedge edge. These two regions also have their own values for the density, the magnetic permeability, the electric permittivity, the wave speed, and the wave number. For each of these parameters, we're assuming that the ones associated with inside the wedge are larger, with the exception of the wave speed. Now I want to take a moment to define the contrast parameter as lambda, which can take any one of these three ratios depending on the chosen physical setting. Now, the title of this talk is has high contrast in it, and by high contrast, we are assuming that the denominators of the chosen ratio are much larger than the numerators. Hence, we are assuming that lambda is small. So now to state the problem. Both total wave fields satisfy Helmholtz's equation. The plane wave source takes this form, and the total wave fields are connected at the wedge faces by these interface conditions. It is here where the contrast parameter comes into play. Now physically, in an acoustic setting, these interface conditions could represent the continuity of pressure and the continuity of the velocity normal to the wedge faces, whereas in an electromagnetic setting, they would represent the continuity of electromagnetic field components tangential to the wedge edge. If you were to create a sum of the incident wave and all reflected and transmitted waves, we would call that the geometrical optic component. And taking it away from the total wave fields creates a remainder term which we call the diffracted component, or phi d and psi d. Both of these which are required to satisfy a radiation condition of this form and this form respectively. Now what this does, this serves as a uniqueness condition. It prevents any solutions that would represent incoming radiation. Lastly, we will have a condition bounding the energy at the wedge edge. Now here, A is a constant and delta hat is the smallest positive solution of this equation here. To keep this presentation brief, I want to assume that delta hat is smaller than 2 so that we can neglect this r squared term. So how do we want to solve this? We want to take advantage of lambda being small and pose this high contrast asymptotic scheme. What this does, this splits the penetrable wedge problem into an infinite sequence of impenetrable wedge problems. Each term in this scheme satisfies the relevant Helmholtz equation and radiation condition, and if we were to put them inside the interface conditions, we could reorganize the results like so. Each and every one of these brackets is required to be 0. Now what this does, this creates a unique boundary condition for every term in the scheme. The edge conditions can also be split up in a similar way by assuming that A and delta hat have their own high contrast expansion. We know more about the delta hat one because of the cotangent equation you saw earlier. The first of these problems, phi naught, is simply the perfect wedge diffraction problem with plane wave forcing, homogeneous Neumann boundary conditions, and this simple edge condition where the exponent is given here. This problem has been known, the solution has been known for over a century now, and there are presently many different methods to solve it, several of which have been reviewed in this paper at the bottom. The rest of the problems are can be split into 2 types. First, there's the psi j problems. Now these, confined to omega 2, have no plane wave forcing, have inhomogeneous Dirichlet boundary conditions where the forcing is on the known phi j component, and the edge condition is simplified to this. The rest of the phi j problems takes a similar form with no plane wave forcing, inhomogeneous Neumann boundary conditions where the forcing depends on the known psi j minus 1 term, and the edge condition is the same as before. What we want to do next is represent the wave fields phi and psi in terms of the spectral functions Sj and Qj by using Sommerfeld integrals. Now this form is advantageous because solutions of this form will automatically satisfy Helmholtz and the radiation conditions, and the exponential kernel is makes this a fast convergent integral because the exponential decays very rapidly on these grey half strips where gamma plus and gamma minus, the Sommerfeld contours, go to infinity. I should also point out that any singularities of these 2 functions will any singularities of these 2 spectral functions should be confined to the vicinity of the real line. I've already mentioned that the first problem has been solved already, and the solution is given here. So, I've talked a lot about the different components of this high contrast approximation, but now I want to show you how we piece it together to create the procedure. So, let's start with the definitions of angles, wave numbers, the contrast parameter, and the first spectral function. We then use them to determine the first spectral function for inside the wedge, which is then used to determine a correction spectral function for outside the wedge, then used to determine Q1, and so on. By the Sommerfeld integrals, each of these spectral functions creates their own unique wave field. Phi naught and psi naught create what we call the leading order approximation, which is then corrected with phi 1 and psi 1 to create the first order approximation, and so on. What I want to show you in the next slide is how we make these connections here. To do this and solve the rest of the impenetrable wedge problems, we use the Wiener-Hopf technique for diffraction in angular regions. This method has been inspired by these two papers. Many of the elements you've seen in Guido Lombardi's talks earlier in the program. Now this results in an integral solution of this form. Here, the green parts are functions of the previous spectral solutions and can have an infinite number of poles and branch buds. The red parts are a periodic set of poles that all have the opportunity to intersect and cross the integration contour. Evaluating these integrals is quite difficult. So I will talk more on this later in the presentation, but for now, I want to talk about a very simple example where the wedge is opened up to create the penetrable half space. Here, the incident wave has been scattered into a single reflected and a single transmitted wave, with the reflection and transmission coefficients R and T respectively. In this particular case, every single integral that I've shown you before can be evaluated exactly, and the resulting asymptotic approximation matches perfectly with the exact solution found using more conventional methods. But what I want to use this case for is as a preliminary test for the high contrast asymptotic series convergence. So, for example, let's take this density plot of the exact solution's real part, where lambda is 0.1, and watch the convergence of the asymptotic series. Leading order, first order, and second order. You can see by inspection that the second order is virtually identical to the exact solution. But if we want to view this convergence much more closely, one must look at the reflection and transmission coefficients themselves, because they're the only part of this particular solution that explicitly depends on lambda. So that is what this left plot is. We've shows the progression of these coefficients as we increase the order of the approximation. You can see that they converge to the true value. This right plot is the absolute error of the left. And this relationship you see here is given in this form, where C is independent of lambda. This means that the asymptotic series will converge provided that C lambda is less than 1. So moving on to a more general situation, the spectral integrals are, well, they're very difficult to evaluate numerically. One can very easily run into complications. For example, in the green parts, summoning the previous spectral solutions can make the computations become slow quite quickly. Now this is because you're using the spectral integrals over and over and over again, which creates nested integrals. However, we only want certain segments of these previous spectral solutions, and a good enough approximation of these segments provides a sufficiently accurate integral evaluation, but is substantially quicker to evaluate. There's also the other danger from the periodic set of poles given by the red parts. Now, I've mentioned before that these poles all have opportunity to intersect and cross the integration contour, and in complex integration theory 101, whenever poles cross the contour, you need to make sure you add the residue to keep the evaluation continuous. However, adding these residues over and over and over again can become quite cumbersome in the code. So we take a little shortcut by using these recurrence relations of this form. These recurrence relations, they're actually the spectral equivalent of the boundary conditions for each impenetrable wedge problem. And we use them as a form of analytic continuation. So, show you what I mean. Take the Z complex plane for any spectral function of your choice, and let's say that in this red strip you've optimized how to evaluate the integral. So if you want to point here, use the recurrence relations to shift it back into the red strip where you've optimized how to evaluate the solution, and then just add on this remainder term. Moving on to the Sommerfeld integrals. Well, despite the fact that this is a fast convergent integral, for the numerical evaluation, it's using the Sommerfeld contours is impractical. Now this is because the exponential kernel is highly oscillatory on these contours. For this reason, that most people prefer to use the steepest descent definition of the Sommerfeld integral, where these blue contours are the steepest descent are the local steepest descent contours. This is much better for us because on these blue contours, the exponential function does not oscillate at all, and the center one is repeated twice in opposite directions, hence it's cancelled out. However, in this active deformation, we will cross all poles in between the black and blue contours. However, these poles have a physical meaning in the wave field. Each pole is a component of the geometrical optic component, and they do still have the chance to cross the steepest descent contours, but whenever this happens, this is a geometrical optic discontinuity. There is also another potential issue. The spectral functions do have branch cuts, and these branch cuts also have the ability to intersect and cross the steepest descent contours. Or if you know when and where this happens, a simple contour deformation will overcome this issue. I'd like to finish by showing you some of our results. Take a right angle wedge where the incident wave is impacting both wedge faces, creating a reflection and a transmission each. These dashed lines are the locations of geometrical optic discontinuities, and these plots are the absolute value of the polar plots of the absolute value of the total wave fields. The left plot has created a reasonable approximation by the third order approximation with lambda being 0.1. And you can see that the right plot has converged much faster with lambda being a much smaller 0.01. There are anomalies, however. You can see here and here, solution doesn't work very well, but I've explained before that in these particular locations, a pole is in the act of crossing the contour. So that's where the anomalies come from. I should probably also make a note, make an important note that obviously the higher order you go, the more integrals you will need to evaluate, the more time it will take to get results. However, the majority of the time taken to make these results is in the interpolations for the integrals, which only need to be done once. After this, creating plots like this takes no time at all. So now, here's another example where we've shifted the incident wave so that it impacts the top face only, and the transmitted wave now impacts the bottom face. For the left plot, the wave number of the scatterer is high enough so it's totally internally reflected, and the right plot has the wave number low enough so it's allowed to be retransmitted. Now, we compare this with an earlier high contrast approximation given by Leolinov in this paper here. Now, in this paper, he finished with a far-field formula for the exterior solution, and you can see here that it agrees very well with our solution, with the exception of this region where the solution has become invalid. Another interesting quantity is the interface conditions. Now, we're pulling in this high contrast approximation, and as we increase the order of the approximation, we're supposed to make sure that the boundary conditions are getting more and more satisfied with each order. So take this is the which you'll recognize as the Neumann type interface condition, and put in the high contrast approximation truncated at J, and it simplifies to what you see here. And it's the absolute value of this quantity that we plot here. The left plot being the top face, and the right one being the bottom face. Again, you can see here that as you increase the order, the error of the interface conditions is converging to 0. So to summarize, we've decomposed the penetrable wedge problem into an infinite sequence of impenetrable problems, and we've constructed a solution to each of them in the form of a complex integral. We've checked this solution with the simple case with a penetrable half space, and we've discussed some efficient and accurate strategies for numerical evaluation. These strategies can still be improved for more extreme cases, however, extreme cases such as grazing incidents or for very thin wedges. We also wish to complete the method of steepest descent to create our own simple far-field formula, like what Leolinov did, except this time we want to accurately create an explicit formula that would efficiently describe headways or lateral waves. And I shall finish here. Thank you for listening.
Who's the boss?
What are the questions? Any questions?
May I ask a completely ignorant question? Simon Chandler-Wilde, he was kind of pursuing hybrid numerical
Well, that's
asymptotic
the
methods.
point of this. The hybrid numerical asymptotic schemes, they work very well for impenetrable scatterers, but they don't work too well with penetrable ones. So the idea here is to create sort of a better understanding of the boundary layers, so we can improve his chosen basis functions for his hybrid numerical asymptotic schemes. That's it.
Motivation behind that.
Right, okay.
This better we need to understand. That's the strategy.
Yeah, so Chandler-Wilde was part of a whole group of people who were looking. They got a lot of money for efficient numerical schemes for high frequency scattering problems, and we always were suspicious. I don't know when I was out of the room, we said this with their ansatz it's not right, and so really you have to get to the very heart of the problem in order to solve it. And then building this into a scheme which has got polygonal structures is really the best way to go, isn't it?
Question. I have two short questions. The first one is, what can you say about convergence of your series? Is it asymptotic, or maybe it's real convergence in some space? And the second comment is, probably if you organize your procedure not by means of Dirichlet and Neumann condition, but more, how to say, accurate, for example, one impedance problem, another impedance problem, then even in the first or in two iterations, you will obtain more accurate results. You will need not 3 iterations, maybe only 1 or 2.
Well, we didn't think about splitting it, or at least I didn't.
Well, because the contrast parameter that Matthew chose naturally led to it being a Neumann-Dirichlet problem, then in some sense this looks the optimal route. But you're right that you could have a problem where your parameter was high contrast, but it didn't come in through the boundary, but came in another way. And in fact, I've been thinking exactly about the same point.
The question is, if you can simulate appropriately reflection coefficient from this side by introducing your small problem, then you will improve even the linear approximation much better.
Yeah, what I did in the actual computations, I did try to actively separate the geo component, because that is the bulk of the behavior, and that with ray tracing methods you can figure out all the directions and all their coefficients. So, but the only reason that I didn't do that is because it could potentially stop the interface conditions being satisfied.
My question was, probably it's possible to show that your iterative procedure converges in some sense, and you show that convergence is due to some, say, maybe Neumann series of your solution. Then in the case when the normal, the operator is less than 1, then you have some natural convergence, something like that. I think it's possible. Probably this is a problem to think about.
We were just happy to see that it seemed to work.
Yeah.
We've not put too much about
But it's
each
only,
other.
I think it's not difficult, but probably this is mathematical question, of course.
Yeah.
There is no doubt that its procedure is correct.
I have a question. In the beginning you said that you have vertex condition in the form of some equation, and as I guess this equation reflects the
Shall I go back?
actual singularity of the field, right?
Here, I'll go back, make things a bit easier.
I think it was slide 2 or 3 or something. So you have sort of cotangent equation, right?
Yes.
And your solutions, the approximation 1, 2, 3, and so on, they have quite different singularities that are singularities of.
Solutions of this.
No, this is a solution. I think this should be a solution of the exact, the singularities of the exact solution, right?
Yes.
Yeah, and your approximate solutions, approximation 1, 2, 3, and so on, they have different singularities. They have singularities of Dirichlet and Neumann wedge, right?
Yes.
They apparently are different. Does it mean that you have got no uniform convergence at the vertex?
But look at that bottom equation there when lambda's large or small. Then it reduces down to the same assumptions that go
It
in.
will be close but not equal.
Yeah.
So does it mean that very, very close to the tip you have some problems with convergence?
Well, we didn't really look too close to, we didn't make any near field approximations. We concentrated more on trying to find far field ones. So maybe that's.
Yeah, well, that's definitely worth checking, because basically we expanded this solution in terms of lambda as a tellus.
I don't think that it spoils the general solution, so I have just theoretical question.
Yeah, I've checked. I have checked the individual wave fields, or rather their spectral path, to see if the equivalent behavior in the spectral domain seems to match up. But when, in terms of piecing it together to see the entire thing, I haven't done.
Okay,
But maybe that's.
I think I understand this.
I think we could try it. Instead of fixing R and changing
Yeah.
theta, you can fix theta and change R and see how it
I'm
goes.
pretty sure those boundary graphs I've shown you, they went pretty close to the, yeah, I think,
Yeah, R equals 0.
well, technically those didn't start at 0, they
Yeah.
started at around 0.1, if I recall.
And this actually refers to Mikhail's question, because if you use slightly impedance condition, you can try your impedance in such a way that you, from the very beginning, you have a correct tip behavior. And probably in this case, as Mikhail says, you will get, this is the precise value at which you will get a better convergence.
Adds to your future. Thank you.
Let us end this piece again.